Assalamualaikum and a very good day to everyone. My name is Nur Amirah Shamimi binti Makno, metric number AN180157, year 4 taking Bachelor of Civil Engineering Technology, major in Environment. I'm going to present my PSM2 poster with the title of First Stage Reusability of Zinc Oxide Clay via MPR, which is Membrane Photocatalytic Reactor for Pomse treatment. Before that, I would like to thank my supervisor, TSR Rizibin Awang, for his assistance and dedicated involvement in every step throughout the process from PSM1 until PSM2. This project would have never been accomplished without his guidance and support over this period of time. The studies are based on pre-treated pomse, or known as Pomse, could not be discharged to the watercourse as it does not comply the discharge limit set by Department of Environment, which is DOE, while advanced Pomse treatment such as photocatalysis required high cost for larger scale application due to increasing the chemical usage, but can reduce the BOD, COD color and turbidity well. This study used membrane photocatalytic reactor, which is MPR, with zinc oxide clay as photocatalyst and examined the reusability of zinc oxide clay. The result, zinc oxide clay can be reused at least 2 cycles with better performance in removing BOD, COD, turbidity and color. For introduction, Malaysia is second largest producer of palm oil in the world. The production of the palm oil leads to huge amount of wastewater generation, known as palm oil mill effluent, which is POME, while the Pomse is produced from the secondary biological treatment of POME, and also known as advanced treatment. The study report on the reusability of zinc oxide clay for Pomse treatment via membrane photocatalytic reactor, which is MPR, and MPR is the one of advanced treatment using a photocatalysis process for the decomposition of organic pollutant. One of the advantage of zinc oxide clay is it can be reused and recycled. For the reusability of zinc oxide clay, the oven drying method was used as it is the most efficient method, and zinc oxide clay was characterized before treatment and after treatment using FTIR, XRD, and the quality of treated Pomse, which is the COD, BOD, turbidity, and also color, was evaluated. The objective of this study is to synthesize the optimal ratio of zinc oxide clay at optimum condition via precipitation method. Next is to evaluate the reusability and performance of zinc oxide clay in the first stage, which is cycle 1 and cycle 2 for Pomse treatment via MPR. And last is to characterize zinc oxide clay physiochemical properties and after treatment, which is 2 cycle of reuse. So I'm going to present my literature review. To validate my research, I have compared and refer to articles with similar experimental, which I compare my findings. The article from Ziad et al. 2020, Akari et al. 2016, and Lucas Gill et al. 2020 are used zinc oxide supported with clay, such as kaolin and also bentonite, in photodegradation and removal activity. The next article by CD et al. 2020 are using zinc oxide, zinc propan separators in treating Pomse. And all the article responds good performance of zinc oxide photocatalyst with the support material. The next table is about the reusability photocatalyst. The article from Zainuri et al. And Vermeulen et al. Used zinc oxide, while article from Mendes et al. Was used zinc oxide and also titanium oxide. Based on these 3 articles, the oven drying method is the best reusability method for the photocatalyst. Okay, next I would like to proceed with methodology part. For synthesis of zinc oxide clay, the precipitation method was used. For this step, a specific amount of clay was added to the zinc oxide clay mixture after a few minutes of reaction to form the zinc oxide clay. After that, the mixture was stirred at room temperature for several hours. Then it was filtered and dried for 1 hour at 100 degrees Celsius in an oven. The precipitate was calcined for an hour at 550 degrees Celsius in the furnace to remove the impurities. I started with permeability test, where the test was conducted from 3 bar until 6 bar. Next is run the photocatalytic reactor with 1 liter Pomse and 0.6 grams zinc oxide clay for 30 minutes with 250 RPMs. Next is run the photocatalytic reactor with UV lamp for 20 minutes. And lastly is pump into membrane with pressure 6 bar and record the volume for 3 hours with 5-minute interval. For reusability method, the zinc oxide clay with excess of Pomse in the photocatalytic reactor will be collected and filtered, and then it will be oven drying for 100 degrees Celsius for 5 hours. For characterization part, the chemical bond of the zinc oxide clay were characterized by using FTIR. FTIR spectra were recorded in transmittance mode in the Eglin technologies, carry 630, while the purity of while the purity and the crystallinity of zinc oxide clay sample were analyzed using SRD. And for the quality of treated Pomse, such as BOD, COD, turbidity, and color will be analyzed for each cycle by using standard method. Color will be determined by using HDR 6000 spectrometry, while the turbidity of treated Pomse will be determined by digital turbidity meter. For BOD measurement, two samples of treated Pomse for each cycle will be collected. One sample will be tested immediately for dissolved oxygen, as shown in this figure. And the second sample will be incubated in the dark for 20 degrees Celsius for 5 days and then test for the amount of dissolved oxygen remaining. The difference in oxygen level is the amount of BOD. For COD, HDRB 600 spectrometers was used to analyze the concentration of COD of the treated sample. The range for the spectrometer is 1600 milligram per liter. The high range COD vial was used in this analysis because the concentration of COD of Pomse was high. So next I will proceed with the result. So this is the FTIR spectra of zinc oxide, and this is the FTIR spectra of zinc oxide clay at 0 cycle and 2 cycle of reuse. So the broadband of 3417 was for OH stretching vibration indicating the presence of hydroxyl group in the commercial zinc oxide, while zinc oxide clay revealed the stretching vibration of structural OH group at 3700. Then the appearance of less intense peak at 2360 then for commercial zinc oxide correspond to presence of CO2, while for zinc oxide clay and zinc oxide clay after 2 cycle, the broadband at 2150 and for both. Next, the strong absorption peaks at 1039 and 1032 bands for zinc oxide clay and zinc oxide clay after 2 cycle of reuse could be attributed to amide bond from the carbonyl group in the presence of kaolin responsible as the capping as well as the reducing agent. While the broadband at 1490 represent of CO group in commercial zinc oxide. The broadband at peak of 682 in commercial zinc oxide correspond to the presence of vibration mode of zinc oxide bond, while the sharp peak of 790 and 782 for zinc oxide clay and zinc oxide clay after 2 cycle. The FTIR spectra of 3 different zinc oxide clay photocatalysts was almost the same peak in the same range. It shows that the zinc oxide clay synthesized using the precipitation method did not change their molecular component and their structures. And for XRD, the result of XRD pattern correspond well to the standard word structure at planes, which is 100, 002, and 101. The sharp and narrow peaks indicate that the zinc oxide clay nanoparticles have good crystallinity. Different diffraction peaks at 2 theta, which sign the zincite and zinc oxide pattern. The presence of different peaks such as 100, 002, 101, 102, 110, 103, 200, 112, and also 012 confirm the hexagonal wizard structure of the zinc oxide powder. And from the graph, no other peaks associated with impurities were detected, which confirm the high purity of the wizard phase. And the use of kaolin in the synthesis of zinc oxide nanoparticle did not affect the crystallinity and the impurities of the photocatalyst. While for the color, The bar chart shows the percentage of the color removal after photocatalysis and the UF membrane for cycle 1 and cycle 2. So the result revealed that the UF membrane was able to remove color better via MPR compared to photocatalysis alone, indicated by high color removal percentage for Pomse. This could be due to the ability of ultrafiltration membrane to separate fullerene from purified water and thus increase the removal efficiency. While the while for the photocatalytic treatment of Pomse in the presence of zinc oxide clay in the first cycle show the poor color removal percentage, but it improved in the second cycle. The enhancement of degradation efficiency in the presence of the sufficient amount of catalyst in the solution is obviously due to the increase of the active material, and thus the zinc oxide active sites result in enhance the free hydroxyl radical generation. For the normalized flux, figure depicts the normalized flux of membrane for Pomse treatment with the first and second cycle of zinc oxide clay reuse in the MPR system. So this is the normalized flux for this first cycle, and this is for second cycle. So maximum normalized flux is about 23 percent was recorded in the second cycle of zinc oxide clay reuse, followed by first cycle, which is 14 percent. The greater permeate flow for Pomse could be attributed to the photocatalyst, which provide a larger surface area for photon absorption and produce free hydroxyl radical to break down Pomse molecule. The greater permeate flow for Pomse could be attributed to the photocatalyst, which provide a larger surface area for photon absorption and produce free hydroxyl radical to break down Pomse molecules according to the trend. So the improvement in the normalized flux of Pomse may be due to increase in the permeate flux, which led to minimum fouling tendency on the membrane. For the result obtained, it was clear that the presence of photocatalysts with larger surface area could improve and maximize the fouling tendency when treating Pomse in the MPR system. So next is COD, BOD, and turbidity. So this is the graph of COD, BOD, and turbidity removal percentage treatment for first and second cycle of zinc oxide reusability after photocatalyst. The reusability of zinc oxide clay photocatalyst in the second cycle result in higher percentage of COD, which is 29.85%, BOD 69.632%, and turbidity removal at negative 7.61 of Pomse. Compared to the first cycle, the COD is 21.32%, the BOD is 69.6%, and the turbidity is negative 104.82%. So the zinc oxide clay for cycle 1 and cycle 2 have almost same percentage of BOD removal, while for percentage of COD removal, zinc oxide clay at second cycle show a better performance compared to the first cycle. And for turbidity removal, the data between the zinc oxide clay at cycle 1 and cycle 2 show a wide gap, which still zinc oxide clay and at two cycle have the higher percentage removal. So this is the bar chart of COD, BOD, and turbidity removal percentage for first and second cycle reuse second cycle of zinc oxide clay reusability after UF membrane. So based on the graph, the Pomse treatment after membrane is second cycle of zinc oxide reusability result the higher COD and turbidity removal percentage with 94.25% and 98.47%. Higher BOD removal percentage of 82.61% was obtained in the first cycle through through the comparison between these two cycles, the photocatalyst reusability, the data did not show significant difference. Okay, next I will move for conclusion. So the XRD result revealed that zinc oxide clay having the hexagonal reset crystal due to less intense peak in the range of 30 degree to 70 degree. The synthesis of zinc oxide nanoparticle with clay did not affect the crystallinity and the impurity of the photocatalyst, and the zinc oxide reusability show a better performance when more cycles were applied. So this is the reference of my project. So that's all from me. Thank you.